BSides DC 2017 videos are brought to you by Threat Quotient, introducing the industry's first threat intelligence platform designed to enable threat operations and management, and Data Tribe, a new kind of startup studio co-building the next generation of commercial cybersecurity, analytics, and big data product companies.
So good afternoon, my name is Daniel Bohannon, and today we'll be talking about Revoke obfuscation, kind of looking at some of the depths of PowerShell obfuscation and how we can use science to detect it. A quick blurb about me. Again, my name is Daniel. I work for Mandiant here in DC. So it's nice to be at a local conference here. The commute was awesome. I've been with Mandiant for about 2.5 years. Started out doing IR consulting for almost 2 years, and I've recently switched to an applied security research position. So I really focus heavily on obfuscation, evasion, and really applying detection at scale to all of our clients and customers at FireEye Mandiant. And there's my Twitter handle there. I want to give a huge shout out to Lee Holmes. He's not here today, but we both did this research together, and Lee is just an awesome guy. He's a lead security architect for Azure over at Microsoft, and he was actually one of the original PowerShell developers. So it's pretty cool to be talking about PowerShell and writing PowerShell tools with the guy who literally wrote the language. It also is very humbling to realize how little I know about PowerShell, but fortunately he's a really humble guy, so he let me know gently the things I didn't know, and I'm a better person for it. So what we're going to talk about today is kind of looking at a treatise on blue team follies. As a blue teamer, I've made all these mistakes, and I hope to share them with you in such a way that you can take it and learn from it, and then some of the cool new stuff that Lee and I spent several months on this year to try to tackle this problem of detecting obfuscated PowerShell. At a very high level, when it comes to actually investigating attacks where PowerShell is used, which PowerShell is used in almost every single investigation I've ever been a part of, because it's native on Windows 7 and later. Attackers love it. Copy and paste is easy. There's tons of PowerShell, offensive PowerShell frameworks out there, and so attackers are using it a lot. Also to be noted, there's a ton of blue team PowerShell frameworks out there that defenders are starting to pick up on, so a lot of really good things on both sides of the fence. But when it comes to actually investigating attacks where PowerShell is leveraged, at the very least, you want at least command line argument information. So you can get that from your security log, 4688 or sysmon EID1. The really juicy stuff you want, though, is at the bottom, which is PowerShell's specific logging, particularly PowerShell 5. And this is a blog post from Microsoft and one at the bottom from one of my colleagues at FireEye, basically looking at kind of what are the benefits you actually get with PowerShell 5 and how does it actually stack up against this kind of obfuscation that we'll be talking about. So, how might an attacker break our assumptions when it comes to detecting PowerShell? Well, let's say that we're going this route of looking at PowerShell.exe when it runs and looking at its arguments and looking for malicious things. Now, obviously, echoing out the word success is not malicious, but I'm just kind of showing in a really small example how you can get code to execute and maybe undermine some of our assumptions about it appearing in argument logs. So in this case, typically you'll see command or something else launching PowerShell, and then you have your command that follows. And you see it runs perfectly fine here. However, you don't have to actually specify the PowerShell command in its arguments. If you just look at PowerShell's help, you can actually push stuff in as standard input. So you can do something like this and have command echo your command, your PowerShell write host, and then pipe it into PowerShell dash or PowerShell IEX input. And PowerShell runs it just fine. Now, why might this matter? Well, as you can see at the top, PowerShell's arguments only contain that dash or that IEX input. But the actual command itself, if we were looking for write host success foreground green, then that's actually in the parent process. So we've just shifted arguments into the parent process. So as a defender, if all your rules are based on PowerShell's arguments, then this might get by you. So maybe we start to look for any processes that have pipe followed by PowerShell. Well, the problem there is that depending on whatever process you're launching it from, you can obfuscate in that process's language and kind of start to stack different languages of obfuscation. So the example at the bottom, I'm basically chopping up power and shell into two command variables, which are process level environment variables, and then echoing it into P1 and P2 such that you can see the parent process has pipe P1, P2 and not pipe PowerShell. So that rule wouldn't really work if we were looking for pipe and then PowerShell. And we actually see attackers doing this in the wild. This is from mid-February this year. This is from a financial threat actor known as Fin8, where they're basically at the very bottom, you can see they had this PowerShell command. They were putting in one environment variable called Microsoft Update Catalog. The second environment variable, they had PowerShell dash, and then they were echoing var1 into var2. which looks really, really familiar to what we were just talking about. And they were launching all this from a WinWord, or from a Word macro, so you actually didn't see a lot of this on the command lines, which was really, really interesting. Another way that we can basically kind of move pieces of information around and keep it off the command lines is through just straight up process level environment variables. Kofter is a really popular piece of malware that does this, typically launched from obfuscated MSHTA and run keys and stuff like that. But basically you'll see PowerShell invoking with IEX the environment variable, some random name environment variable. Now typically we'll see $env : to reference environment variables, but there's tons of ways. At the bottom is just some of the few ways that are really uncommon, but that you can actually extract environment variable values out. Another way that we could do this is we could basically pipe our arguments into clip and then just pull them off the clipboard. So maybe we're thinking, why don't we just look for these arguments in PowerShell.exe and then in its parent process? So the problem there is, what if we introduced a third process in the mix? So instead of command spawning PowerShell, what if we said command setting the arguments into environment variables, and then a second command echoing those environment variables into PowerShell, and then PowerShell launches it? Well, so technically this works, but we don't get any benefit out of this because, as we can see, we still see the full command in the parent process. However, if we take notice of this pipe, if we escape it one layer, and this isn't PowerShell, we're doing command level escaping. So we want to escape it for the first command, but not for the second one. And if we do that, then we're golden. PowerShell runs with nothing in its arguments about what happened, and the parent process only has the name of the process level environment variable and not the contents itself. So we'd actually have to go all the way up to the grandparent process to get this. And this is kind of a tree structure or a little outline of what this looks like. So maybe we can say, okay, well, why don't we just take any PowerShell process and recursively go up the stack all the way to see all the arguments to see if any of them contain these malicious arguments. Well, the only problem there is that there's tons of ways where you can pass information back and forth with no actual relationship between the processes themselves, or no recursive relationship up. This is one example of basically spawning command where pieces of code are stored in the title of each command window, and then WMI is used to query them out and reassemble them back together and then invoke them. Clipboard is another example. You could use user-level environment variables. You could pass information back through a file or registry. There's tons of ways you can pass information back and forth such that it won't show up on the command line as you'd expect. So the good news in all of this is that PowerShell script block logging catches all of this. No matter how it's run, no matter how it's passed in. PowerShell 5 is just insanely awesome in terms of the preventative and detective security controls that are in place for a scripting language. It's stupid awesome. The bad news is that there's token layer obfuscation that persists even into these script block logs. And as you'll notice as we go, this PowerShell shield in the top right, each obfuscation technique that we talk about, when that shield shows up, that's saying, hey, no matter what else may have missed it, this is going to show up in PowerShell logs. Now, it may look slightly differently than you'd think, and I'll try to basically touch on those cases, but it's really, really awesome to have that kind of data available. So let's look at an example of obfuscating a PowerShell command in some really crazy ways. So we're going to start with the cradle, or the remote download cradle, which is basically this one-liner command, which is in-memory execution of some remotely hosted PowerShell script. Attackers use this all the time because frameworks use this all the time, and we all like to use frameworks and copy and paste code from one another. So Veil, PowerSploit, Metasploit, you name it, we see this all the time. So let's kind of play red team, blue team, which is kind of how I define my life, basically, of basically breaking my assumptions as a defender, and then how can I bolster those assumptions. So at the top, we have an attacker command, which is this remote download cradle with this bit.ly link, which is totally legit. And then let's say as a defender, if we want to catch this on the command line, how can we do that? Well, we can start to build out a list of terms at the bottom, where if we see invoke expression, new object, system.net.web client, and then download string HTTP, this would catch this exact command. So now let's go through and see how we can obfuscate the command at the top and adjust our defender terms at the bottom to kind of stay head-to-head with what the attacker is doing. So first of all, system. Is not necessary almost anywhere you see it in PowerShell. PowerShell is going to automatically pre-pin that underneath the hood, so an attacker doesn't have to put system. So if an attacker doesn't absolutely have to have this in their command, then I don't want to make that assumption as a defender, so I'm going to pull it out of both. The URL in this case is just a string, and it's a string token. We can do things like concatenate it inline. We're also not really limited to double quotes. We can use single quotes, white space, push it around, stuff like that. We can also set it as a variable. So let's go ahead and move that HTTP from the download string portion. Download string. Now, this is the most common method that we see. So download string, let's kind of take a step back. New object net.web client is creating a .NET class for the net.web client class, which has many methods. Download string is just one of them, but there's quite a few. Download string, download file, and download data are some of the most common ones that we see. Download file will hit disk, so it's more used in commodity. But download string and download data, data will be a byte array as opposed to an expression itself. But maybe we can just say, okay, why don't we just say .download and we'll catch all of these. So let's do that. So now, for this .download, how might this little parenthesis bite us if we have this as part of our detection? Well, you can actually take new object net.web client and you can set it in a variable and then have variable .download string. Typically, you'll see some frameworks calling that variable WC. So you have variable name .download string. There's no parenthesis. So let's go ahead and remove that from the arguments at the bottom. Now that dot, what could an attacker do to make this dot really problematic for us as defenders? Well, they could put single quotes around download string. This doesn't make it a string, but it still breaks that dot. But then we can put double quotes around it. And what I found is that if you have double quotes, if you look at download string, what you can actually do is then put a tick mark in download string, and it still runs. Crazy, right? Now, why does this work? Well, the tick mark is the escape character for PowerShell, and it has meaning behind these escapable characters: 0 for null, B for backspace, new line, all this kind of stuff. But if you escape something that has no escapable meaning, it just runs it. And this is not just true of PowerShell. If you do the same with command with a caret, if you escape something that doesn't have any meaning to be escaped, it just doesn't do anything, and it goes ahead and keeps on running. So you can put a lot of tick characters and a lot of tick marks there, as long as you stay away from those special 8 characters that have special escapable meaning. But if you're like me, you really want to put tick marks in front of those characters. So all you have to do then is just uppercase them, and then you're good to go. So now any method, we can put double quotes around it, put ticks in front of any character that we want, as long as it's not a 0, because unfortunately there's no uppercase 0. So, out of luck on that one. But the problematic thing from a defensive perspective is that this persists on command line arguments as well as all the way into the script block logs, which is PowerShell. It's the latest and greatest 4104 EID, really, really awesome, really sexy logs, but these tick marks are still there. And if you'll take a closer look, you'll see the concatenation is still there. So at the end of the day, script block logging will basically log every kind of layer of the onion. If you have this command encrypted and encoded like 100 times, every layer gets its own script block logging. Even if you're running something remotely, even though you'll never see that in the command line arguments, it'll all show up in PowerShell script block logging. But this token layer obfuscation will still persist. So how do we deal with this as defenders? Well, we're not done yet. We could try to regex all the things, right, and basically take into account any tick marks. If we go that route, I would recommend also adding open read, because we looked at download string file data. Open read's another one that returns a byte stream instead of a byte array, and we've seen attackers use this a couple times, but it's not too common. So if you want to go that route, make sure you have .download and .openread, but I would advise against it, because if you put parentheses around any method, then you can actually treat it as a full-blown string. So as strings, you can basically concatenate it, reorder it, do a ton of crazy stuff. And in this case, you'll also see there's this .invoke after that method that's only required in PowerShell 2. PowerShell 3 and later is smart enough where you don't need that .invoke. So a lot of the obfuscation frameworks that I've worked on, I make sure to include that .invoke by default, so it works on any version of PowerShell. But as a defender, I want to make sure that we're not focusing on that .invoke for detections, because it's not necessary in later versions. So let's just remove download string from our defensive kind of list. All right, net.web client. For this, we can put double quotes and ticks. We can put parentheses and, again, treat it like a string, concatenate it, reorder it, chunk it up into small pieces, whatever we want. So we'll just go with the first option and say, yeah, let's just go ahead and get rid of net.web client from a defensive perspective and keep going. Now, new object. So we're left with the two pieces we're left with are invoke expression and new object. And these are both commandlets. Now, PowerShell is super, super friendly and inviting to people who have never written PowerShell before, because it has tons of aliases, which basically means PowerShell has a commandlet called getChildItem. And if you want to list everything in a directory, you just say getChildItem on it. But if you have no clue what PowerShell is, then you might just type dir, and it will also work, because that's an alias for getChildItem. If you come from a Linux world, you can just type ls, and that works, because they have all these aliases that translate into the thing you actually mean. And then there's shortened forms of that, and so PowerShell gives you a lot of options. That's great from a usability perspective, but it's terrifying from a defensive perspective, because now we have to find all these different options and make sure we have coverage for all of them. The good news here is that new object doesn't have any of those. There's no aliases, there's no shortened forms of it, so I was really excited when I came across this and realized this is going to be a really solid detection. The only problem is that PowerShell is too helpful sometimes. So there's so many functions in command that sometimes you kind of forget which one that you're looking for. And so you can basically use git command and say git command, show me all the commands or functions that start with a new -p, and just put a wildcard at the end and it'll list all this information. Now the cool part here is that this is not text that's being returned, it's PowerShell objects. Now why does that matter? Well, we can basically take the result of a single, if we basically have it return just a single commandlet, we can then pass it into invoke expression, which will automatically convert that object into the string of new object and then invoke it. But we can actually be more creative since we're dealing with objects. Instead of invoke expression, we can use a dot or an ampersand, which are invocation operators. Now here's where this gets really fun. To move those wildcards, as long as we're returning a single object, this works, and this is new object. So instead of specifying new object on the command line, we could actually replace that T with a wildcard, or keep replacing a lot of characters, and as long as we have a query that will return only a new object, that's now new object. And that doesn't appear, you will not see new object appearing on the command line arguments or in script block logs. The one place you will see it though is in the 4103 EID, which is module logs. So basically think about any kind of huge script, and module logs are the ones that I've not found really good ways to obfuscate it. But the problem is that if you have a huge script, you can have hundreds or even thousands of module logs for just a single execution of a script, because it's looking at every commandlet, every parameter binding, all this stuff. So really, really helpful, really robust, but a lot of logs. So how do we actually meaningfully piece that back together to detect this kind of stuff? Well, we're not done here. Git command also has an alias of GCM, and there's actually an undocumented alias called command, because PowerShell will automatically basically take git dash and prepend it to anything you do to say, I didn't find, when you type the word command, I didn't find a function, I didn't find a commandlet. Maybe you meant git dash command. Oh, you did. That's what we're going to do. So again, rewind every detection that we've ever built as a defender for PowerShell commandlets that included git dash. We totally don't need git dash. So we want to make sure that we don't define that in our detections. Otherwise, we can get burned on this. Another thing we can do if we don't want to use wildcards, we can always just say, basically take our commandlet name and chop it up into substrings or whatever we want, and then specify it there with git command. These are several different PowerShell 1.0 syntaxes for doing this exact same thing. If you ever look at poshcode.org, it's one of the first PowerShell gallery-like distribution kind of sharing platforms, and it's been around for a while, which is awesome because there's a lot of PowerShell 1.0 syntax, which still works today, but no one really is using it because it's really verbose like this. Well, if you're an attacker, it'd be great if you could find some things that no one is familiar with and no one's looking for, because this might do exactly what you need, but no defender's looking for it. So if you notice this execution context, that's an automatic variable within PowerShell, and we're going to see this coming up again and again, so you want to make sure you're looking for that. For all this stuff with git command, we can do the exact same thing with git alias, but instead of dealing with the full commandlet name, we're dealing with the alias name itself. So we have git alias, it has an alias of gal, and then git alias's alias is called alias because of the git dash beforehand. Make sense? All good? All right, let's keep going. So maybe we'd add all these things. Maybe we say, okay, I'm going to look for new object, I'm going to look for git command, GCM, git alias, all this kind of stuff. And at the end of the day, it's not really going to be feasible to find all this, because whenever you can get any piece of a command into a string, then you're golden. You can manipulate it in all kinds of crazy ways. But if we did want to go down this route, we'd have to keep in mind you can put tick marks in front of all these things. You can also use the, you can just, instead of using git command, you can use those invocation operators again and just start to treat the commandlet name as a string. And so on the left we have concatenation, on the right we have reordering. And then reordering is really, really awesome, because some people will say, okay, well, concatenation I don't care about, because whenever I look at logs, I remove all the white space and special characters such that new object will come back together, and then I evaluate at that point. Well, when you do things like using the -f format operator and start to reorder commands, new object will never come back together no matter how many special characters and white space you remove, because it's absolutely reordered. And this is where it gets really, really challenging. So let's just give up on this. Be a realist here. So we're left with invoke expression. Now, as a defender, if you don't know where to start with PowerShell and you have command line logs, look for IEX and invoke expression. Pays crazy dividends. That's like the best place to start. Just start there. So what's problematic about invoke expression? Well, you have the alias of IEX. The ordering doesn't matter. You can have it at the beginning or at the end of an expression. You also can put tick marks in it because it's a commandlet like anything else in PowerShell. You can use the invocation operators and start to concatenate or reorder IEX and invoke it with the dot or the ampersand invocation operators. Then let's step back and say, okay, well, why all these ways to execute code in PowerShell? This seems really problematic, right? And what we'll talk about in a second is Lee and I basically assembled this huge PowerShell corpus of scripts to kind of study what's normal and what's not in terms of finding evil, which we'll talk about in just a couple slides. But basically 3% of scripts in the wild use invoke expression in the script itself, which sounds like a small percentage, but it's actually a lot of scripts out there. So you can't even feasibly say, I don't want to let invoke expression run in the script context. But again, on the command line, it's pretty uncommon. But then you have its cousin, invoke command. Now, invoke command is typically used to run a command on a remote system, and it's expecting a script block, whereas invoke expression is expecting an expression. But if you don't specify a remote system, it runs locally. So you have invoke command, ICM.invoke, or invocation operators. You also have invoke return as is, invoke with context, tons of things out there. So, okay, let's say we're adding this to the list of like invocation options, right? Well, we also have PowerShell 1.0, where there's that execution context again. We have invoke script. But really, what I'm worried about is how do we deal with this ampersand and this dot? How can we feasibly look for this on the command line without getting insane false positives? Well, in this case, we're dealing with script blocks. So maybe we say, if I see a combination of an ampersand or dot, and I see the left and right braces, which is what you have to denote script blocks, then maybe we're good. It would help with false positives, but at the end of the day, you don't have to have curly braces to define script blocks. You can actually convert expressions to script blocks using, these are two options here, using the script block .NET class with the create method, or PowerShell 1.0 syntax again. And then for each of these, you can apply all the obfuscation we just talked about and get crazy results there. So there's still no silver bullet at this point. Kind of sucks. Invoke Cradle Crafter is a tool that I released earlier this year, and it has these are all the memory invocation options, but it has over 10 different invocation options that will randomly go and generate, including some of the ones we looked at, and then some other crazier ones. So if you want an idea of some of the crazy things you can do to basically form invoke expression or IEX to invoke PowerShell code, then this is a tool that you can use just to randomly generate that kind of syntax. Whew. All right, take a breath. That was a lot. I've been droning up here for a while. The good news is that this is really the extent of how you can obfuscate PowerShell. The bad news is that I'm totally kidding. There's a lot more you can do. So if we have our command, we just did all that, right? All this crazy tick marks and wildcards and all this stuff. Well, what if we just said, let me treat the entire command as a single string and then invoke it? That means I've got the entire command as a string, so I can do crazy string manipulation on the whole thing. Like maybe we'll just reverse the entire command. And on the command line, it's in reverse, but then in memory, it re-reverses it and we invoke it. You can also put garbage delimiters just all throughout the command and use the split command to basically pull out those delimiters. You can use replace operations to replace the delimiters with nothing. You can then just do straight up concatenation and basically chop up and reorder your command into a lot of pieces. So these are some options that, again, are going to evade command line stuff, but it's going to be reassembled for everything in script block logs. So script block logs are going to have it all put back together, which is really, really nice. So, wouldn't it suck if someone wrote a tool that did all this stuff automatically? As defenders, we'd probably hate the person who did that, right? So, unfortunately, this is what I got myself into last year, and I released this tool called Invoke Obfuscation that basically took all this research that I did and automated the obfuscation of PowerShell code. Any arbitrary command or script you feed in, it'll basically give you the whole slew of options of what you want to obfuscate. So, in this case, if we take the exact same one-liner download Cradle that we just walked through, then at a push of a button, we can have it produce something like this, which is going through and reordering all the components and invoking it with invocation operators and stuff like that. But then we can take that and say, let me treat the whole thing as a string and do something crazier like this, and just reorder the whole command as a string. Now, I put this flag up here because a couple months ago we saw APT32, which is a Vietnamese threat group, using my tool to do their nefarious activity, and they actually wrap their commands in like a lot of layers, like at least 5 or 6 layers of this like string manipulation stuff. So I get a lot of dirty looks in the office when those samples come in, and they just kind of slide that over my way for me to go and decode. So people say you should eat your own dog food. I do a lot, and the dog food doesn't taste that good anymore. So hold the tomatoes. Then earlier this year, I released Invoke Cradle Crafter, which is not taking any arbitrary code in. It's basically saying, feed me a remote URI and any post kind of Cradle commands you want to run, and then let me show you some really weird Cradle syntaxes you can use that maybe defenders aren't looking for, and that hopefully defenders will use to start looking for them. And so anyways, we take that same URI of Bitly legit, and we can produce something like this. Looks totally different than Invoke Obfuscation. There's no tick marks. It's basically doing like method and member and commandlet enumeration to basically produce strings like download string out of this like crazy, just long and nasty command. So then you can do something like this and just say, well, who needs alphanumeric? So we just use special characters. Now I got to say, the guy who came up with this concept is a Japanese researcher who in 2010 wrote Hello World in PowerShell with nothing but special characters. The Twitter handle is Muraguchi, and it's just a fascinating blog post. Google Translate it if you don't speak Japanese, because I don't. But basically took 3 steps into taking special characters and coming up with any arbitrary PowerShell code. It's a really beautiful idea, and this produces not beautiful code. But at the end of the day, it's a ton of variables that are all stored in $ curly braces, because when you put curly braces, you can put special characters as variable names. So you could also put white space as the character names and get something like this. And I was talking with Casey Smith, or Sub-T, early this year, and he said, oh, that reminds me of white space encoding. And I said, I don't know what that is, and you got to tell me about it. And so he said, oh yeah, you just take white space and tabs and basically do that for the encoding. And so I was like, oh, sweet. And so I wrote this. And so this is that same command where the whole command is either white spaces delimited by tabs or tabs delimited by white spaces, and you have the stub decoder at the end. Now, for both of these options, again, it is completely reassembled in script block logs. You don't need anything fancy to detect this in script block logs because it all comes back together magically. It's a really beautiful example of the power of script block logs. But let's say you don't have script block logs. Then maybe you're looking at me and saying, wow, I really feel like there's no hope here. What could we possibly do? So this is kind of the turning of the tides of this talk. Hopefully all the depressing stuff is out, and let's talk about some good news for defenders, right? So let's try to do a little science. Now, I'm not a data scientist, and nor do I try to pretend to be one. But there's some simple statistical analysis techniques that we can perhaps apply to this problem area and get some good results out of. So as a human, if we look at this code, no one here would look at this code and say, yep, let's let that ride on through my environment. Like, totally okay to run that. As humans, we can look at this and say, this code is not well. So how might we tell a computer to figure that out? So one of the first things last year, almost exactly a year ago, it was a couple weeks after I released Invoke Obfuscation at DerbyCon, Lee Holmes wrote a blog post called Detecting More Obfuscated PowerShell. And he actually referenced these examples in the blog post, and he did something really, really cool, which actually started this entire conversation with me and Lee Holmes about what other ideas could we apply to detect this kind of stuff, and led to this collaboration, which is kind of funny looking back on. So anyways, he took all the PowerShell scripts off of poshcode.org, which is 3,400 scripts at the time, and he basically did character frequency analysis on all of them. And so on the right is the average of all the poshcode scripts, which, as you'd expect, PowerShell, the language itself is English, and so you'd expect English characters to kind of match like English, grammar and structure and all that kind of stuff. So we see ETA, those are the most common, that makes up 20% of all the PowerShell scripts. The first special character we see is the $ at 3% on average. 3% of any PowerShell script on this site is a $. Now you look on the left. There, it's insane. 20% is tick marks. 8% for all this stuff. And then over here, obviously, it's all special characters. It looks really, really different. So again, we can look at that and say, okay, yeah, these are really different, but how do we tell a computer to do that? So this is where we get a little nerdy here for a second. Talk about cosine similarity. Now, I'm not this math whiz person, so if you're not, please don't check out. I'm going to try to make this fun and really exciting. But basically, the concept is, if you have 2 points, 2 coordinates to make a line, right? You have line A and you have line B. And they have angles, right? And so cosine similarity basically saying these lines would be very similar because the angles between them are 0. But if you have 90 degrees, that's like dead different, right? So we can actually extend this idea beyond 2 coordinate lines to 3 coordinate lines, 4 coordinate lines, maybe 26 coordinate lines for all the alpha characters. So that's what Lee did in this blog post. He basically said, okay, why don't I apply this cosine similarity technique and then apply that to all the scripts in Poshcode. And what you'll see is that almost all the scripts are really, really close to the value of 1. So like 95% similar, 97% similar, but then we have our 2 samples at the bottom, which are 37% similar and 15% similar. Now, if we took all the codes on Poshcode and did the scatter chart, we'll see most of them are right up there at 1, really, really similar to each other. But then you have all these really randos just falling out at the bottom. And so what we can do is take 3,400 scripts and immediately just say, let's look at everything below 80%. And that's like 30 scripts. So This is great on just 3,400 scripts, but as Lee and I started to do this research, we said we need a lot of data. We need as much data as we can possibly get our hands on. So a year and a half ago, Microsoft put out this contest called Underhanded PowerShell, basically inviting people from the community to basically submit obtuse and obfuscated PowerShell to evade certain checks. So that was a little bit of data, but then we really wanted a huge corpus of data. So we started with the underhand PowerShell data, GitHub, postcode, all this stuff. But the important thing to keep in mind for us is that Lee and I felt it was really important to highlight that you can actually gather all this data and be really polite in the process. And what do I mean by that? Well, Lee wrote the script to basically scrape GitHub, and all the blue portions are the actual pieces of code that are scraping GitHub, and all the red portions are 100% Canadian. Because Lee Holmes is Canadian, and he's the nicest person you've ever met, and it's just like throttling and all this great stuff. So he basically was basically scraping for like a month. He created a GitHub ID and said, all right, there's 10 million IDs. This should take us a month or something like that. And so anyway, it's getting closer to a month. His script is still running, and he sees 10 million ID, 11 million, 12 million. He's like, wait a second. And he went back and double checked. It was 100 million in GitHub. He's like, oh my gosh, the clock's a ticking. Like, how are we going to get this data? And so apparently the most polite thing you can do is just ask the great folks at GitHub, hey, would you mind telling us what all the PowerShell projects are and zipping those up for us? And on a lunch break, they went and did just that. So kudos to GitHub for getting us that data. This is every single contributor in GitHub that has ever submitted a PowerShell script as of a couple months ago. I just want to ask, has anyone in here ever submitted a PowerShell script to GitHub or TechNet or any of these places? Can you just raise your hand real quick? Awesome. Thank you very much, because you actually are part of this research. Your name is on the slide. Your name is buried in the code in some interesting places. But this wouldn't be possible without all the open source PowerShell scripts that are out there. So seriously, thank you very much. I won't read these right now. If we have time at the end, we'll go through that. So we got a lot of scripts, right? Now, when we have a lot of scripts, we then have to do something with it, because it'd be irresponsible not to, right? So now, if you start looking through all these scripts, you're going to find some weird shenanigans out there. And one of the ones I'd like to highlight was just a really sad one. Remove games.ps1. Someone wrote this to go through and kill games, the running process, even nuke the directory. Really sad, major buzzkill. But in all seriousness, we got a lot of scripts. How many? 408,000 scripts. Over 28,000 authors. And the fun thing that we did, people like to think that hacking is like really cool, Mr. Robot, yeah, it's really fun, like wear a hoodie. At the end of the day, what we had to do was we had to manually label 7,000 scripts, which meant that on weekends, sit in front of the computer and Notepad would pop up, and you'd scroll through the script and be like, yep, that one looks pretty obfuscated. Let's mark that as obfuscated. Next, please, and go through and do that 7,000 times. That's not fun. Now, why in the world would we do that? One reason is so that someone else wouldn't have to, so they could just use the labeling we did. But if you think back here, on this approach of character frequency, if we looked at everything under 80%, then we could say, okay, this was pretty good. Most of what was under 80% is obfuscated, right? What we don't know is are there any obfuscated scripts above that 80% mark? And short of looking at all 3,400 options, when it comes to actually trying to think differently about this and applying some different techniques, we need to actually have labeled data so that we know at the end of the day, did we detect all of the things that we labeled as bad? I'm going to keep going. Ryan Cobb put out a blog post basically taking some of these ideas and applying it, and basically showing that as you start to creep up and look at higher and higher percentages, you're going to deal with more false positives, but that's where you're going to find some more of the wins, some more of the obfuscated scripts that are more similar than not. So how does this character frequency analysis score? The two things to look at here are precision and recall. And it's 89% and 37%. So precision means, let's say we have 100,000 PowerShell scripts, right? And 10,000 of those are bad. They're obfuscated. Now, if we run this tool and it says, okay, these are the 1,000 scripts out of the whole 100,000 that are obfuscated. Let's say every single one it returned, it was correct. Its precision would be 100%. So basically, every time this model says it's bad, it's bad. But it missed 90% of them out there. That would be a really low recall score. It'd be a 10% recall score. So in this case, 90% precision is pretty good, but 37% recall means it barely got over a third of the obfuscated scripts out there. So we need something better. So surely we can do better. So how might we do better? Well, PowerShell there's a lot more features. In the data science community, information retrieval community, they would say these character counts and frequencies are features. So PowerShell, when it looks at itself, it basically sees, I know that this is this commandlet I'm calling a generic. I know that these are left parentheses, right parentheses. I know this is an object, all this kind of stuff. But in PowerShell 3 and later, what became exposed to anyone is what's called the AST, or the abstract syntax tree, which basically looks like this. So not only does PowerShell is it able to tokenize each piece of the command, but it actually knows the relationship of those commands. Now, why does this matter for us? This allows us to get insane features and really focus in. Because you could say, okay, character frequency makes sense. You can have really obfuscated stuff with all these tick marks and have your evil code. And then you can literally just copy and paste the entire work of Shakespeare. And then that's going to really throw off your overall, character frequency analysis because it's going to look like normal English, right? Well, that's the whole point. Why don't we drill down and start to gather features from each kind of commandlet or each kind of token, so that we have to force someone to basically put in bad data in every single place that we're looking. There's a great tool there called AST Explorer, which is just a little GUI where you can basically paste in any kind of code you want and explore kind of how the AST structure is. So with this, we were able to extract things like distribution of AST types. So again, out of the whole script, let's say 90% of this entire script is nothing but commandlets, or strings, or arrays, or stuff like that. So we did just a straight up distribution of those types, assignment, binary invocation operators. We did array size ranges. Again, a lot of arrays aren't that big, but if you have arrays of like thousands of characters, maybe that's shellcode. That's kind of odd, right? And then for every kind of AST type, again, commandlet, string, method, all this stuff, function, comments, we basically did character frequency on each of those individually as well as the entire script itself. So we did character frequency. We also did things like entropy. We did the length, max, min, median, mode, range, average, white space density, character casing. Again, randomized casing in a lot of frameworks. If you see 50-50, uppercase, lowercase, that's randomized casing, because typically it's going to be like 12 or something. All these different things, and we basically pushed them all together so that for any input PowerShell command or script, we get almost 5,000 features, which is a lot more than just the alphanumerics, right? And so we were really excited about this, spent a lot of time just getting as many features as we possibly could. Never once did we say, this feature is bad or this feature isn't. We just said, I just want the data. But then we realized, crap, what are we going to do with 5,000 features, all right? Like, how do we actually, make meaningful use of this data? So basically, what we have here is that of these 5,000 features, some of these features matter a lot more than others. And instead of us going through and figuring out which one matters more than the other, we used a little thing called logistic regression. So basically, you have, and the coloring is a little bit unfortunate, but basically you have a logit function to say, like, again, if you have like thousands of commandlets in one script, but only like 10 comments, like you can't deal with a range like that. So we use something called a logit function to basically bring all the values between 0 and 1 and kind of smush it down on this plot. And then we use linear regression. So what does that look like? Basically, we go through and we take all 5,000 features and we have a weight. That weight is basically saying feature 1 is this important, or feature 2 is this not important, or feature 558 is this important. And so for every single input script or command, we extract all 5,000 features, and then for each feature, we multiply it by its weight to say how important are you. We then add up all those results, and then if it's over a certain point, then it's obfuscated. If it's below a certain point, it's not obfuscated. So now, again, it comes back to, well, how do we decide the values of the weights? How important is one feature over the other? Well, we let the model tell us that. And what I mean by that is we take that labeled data, again, those 7,000 scripts, and we basically, through thousands of iterations, send it through and say, okay, pull out all the features, and we start with all the weights being exactly the same. Everything on a level playing field. And it goes through and it pulls out all the features, does all the multiplications, and it says, are you over 1 or are you less than 1? Are you obfuscated or not? It makes that decision, and then it says, okay, since this is labeled data, I happen to know whether I was right or not. And whenever it was right, it's all good. But whenever it was wrong, it looks and says, okay, what weights contributed the most to me being wrong about this? And then it adjusts those the most, either up or down. And then the weights that were least, it adjusts those the least. And so it keeps kind of tuning and tweaking each thing through thousands and thousands and thousands of iterations. And as you can kind of see in this concentric circle, it kind of gets closer and closer to the truth as it moves all these weights up and down. So how does this actually work at the end of the day? Well, again, remember our cosine similarity, we had 89% precision and recall is 37%. Now, for anyone who's not a blue teamer in the house, this next slide is our equivalent of getting DA. So we're going to get really excited about this. So just to let you in on this. Our model performed at 96% precision and 94% recall, which we were really excited about. And false positives were 0.01. So this model is literally 10 times better at finding obfuscated code with half the false positives. So we're really, really excited about this. Now you may step back and say, okay, well, what about sketchy stuff, right? Like obfuscation is kind of a spectrum, right? Like stuff can be really, really obfuscated, like the thing on the left, where there's just all special characters. But then there can be some other things where it's like, I don't think that's bad, but I kind of want a second look. So we actually went back and kind of labeled things as like sketchy. And if you think about it from this way, it's like if you had the world's best intern, this intern would be the one to go around and say, hey, I don't think this is bad, but I'd appreciate it if you took a second look. That's kind of the approach that we took. And so if we start labeling sketchy stuff, what we'll actually see here is that overall it performed at 88 and 89%. So basically it was wrong a lot, but it actually captured 97% of the evil that was out there as opposed to the 94. So what that means is that if you want like the super high confidence of the stuff that was labeled as really, really obfuscated, then you're going to get that 94%, 95%. And in the tool, that's basically the default. It goes for high confidence first. But then if you want to cast a wider net and say, yeah, I'm okay to get some sketchy stuff as well, I'm willing to weed through some false positives and find some more stuff that maybe I'm missing in the other model, then you can kind of do that wider net approach. So what about other algorithms? So again, not being a data science person, with this labeled data set, you can take this and plug it into any kind of like machine learning studio that you want. So Lee Holmes spent a little bit of time doing this and testing out tons of other algorithms to say like, did our approach actually fare well against all the others? And it actually did. It ended up being almost tied with one of the other ones, but just a little bit better. And so again, you don't have to have some fancy studio like this to do what we're doing. We actually did all of this by hand, and it's all out there open source on GitHub for anyone to be able to take that same data and do cool stuff with it. So, a quick demo of the tool. So there's three parts of the tool. This first one literally has nothing to do with finding evil. It's just all about ASCII art, because who doesn't like ASCII art? So it's colored ASCII art. It's just doing like a quick little demo of like, here's a command, here's some of the kind of extractions, feature extractions that we do. Over 5,000 features, less than 300 milliseconds for most PowerShell scripts, blah, blah, blah. And here's the interactive menu here. So basically the things to keep in mind are you have some options here. One is tutorial, which is a glorified colored README, which who doesn't like colored READMEs, right? So if you don't want to read the README on GitHub, you can just do tutorial. Fun facts, again, we spent a ton of time going through a ton of data, like 4 gigs uncompressed PowerShell scripts. Like it is a lot of data. And there's a lot of fun things that you'll learn about that data, and so there's some fun facts in there, some random fun facts. ASCII art, when you go through that much data, there's some really creative people out there who are way more artistic than me, so we just went and kind of wrote some URL rules to go through and find ASCII art stuff. I spent an entire weekend doing nothing but like on my exercise bike at my gym, like going through ASCII art, like my wife was like, you're such a nerd. So anyways, there's random samplings of ASCII art there you can check out. You can also do a fun set of quotes, and then also credit. So again, every single GitHub contributor for any PowerShell project, as of a couple months ago, your name is in here, and it'll go and randomly kind of display, hey, thanks to these 10 contributors. And there's also a sub-list in there of like our favorite like 300 contributor names, because there's some really creative contributor names. So some fun stuff in there. So now if you actually want to find evil, just throw that out the window and then get to the really good stuff, which there's 2 components here. One is reassembling scripts out of script block logs. So remember I talked about how PowerShell 5 is really awesome and you have these EID 4104 events. Well, they're really verbose, right? And so if you enable this in environments, people are saying, well, we can't possibly index all this data into our SIM. And it's like, well, that's understandable. It's a lot of data. So how can we make meaningful use of it today? Well, if you enable that logging, you can either acquire the raw EVTX files or just use get when event. We include a lot of ingestion options. So basically, you'll take the full event log and pipe it into this function, and it will basically go and reassemble the script out of the script block logs. Because if you have a really long script, then it can be spread across hundreds of script block logs, and this will reassemble that for you. And it returns it all in PowerShell objects, which is nice. So you have PowerShell scripts now, either command line from whatever sources you have. Maybe you have a directory of scripts you've pulled out, off the wire, other things, or you go out and you query your event logs and you reassemble all the scripts, and now you have it in memory. So the last piece is pushing it through the magic, which is measure RVO obfuscation. And here we are chewing through 39 scripts right here and labeling it as obfuscated or not obfuscated. And again, this is basically taking all the scripts, it's extracting 5,000 features, multiplying the 5,000 against the weights, adding them up, saying are you obfuscated or not, and then coming back with the full results of the script, saying true or false, is this obfuscated? It gives the full time of how much it took to extract the features, measure the features, all this stuff. And then also all 5,000 features are listed in that object for every single result. So you have everything at your disposal, whether you want to dump it to disk or do whatever else you want, to start finding obfuscated code immediately. Now keep in mind, this does not find bad code per se. This is obfuscated code. There is still a very, really important role for looking for indicators of compromise in whatever frameworks that you're seeing out there. So I think it's important to add this as a supplement to we're looking for these known bad syntaxes or module logs or other things like that. And then for everything else that we're possibly missing, just run this against it and see what it comes up with. So the very last thing I'll say is that Lee and I, we really wanted this tool to be used by anyone. We want anyone to, after the whole really discouraging first part of this talk, from a defensive perspective, be able to say, yes, like there's a tool we can actually start using today. And to be able to go back to your organizations and say to your manager, hey, we really need to get to PowerShell 5. And they say, why? And you say, well, there's crazy obfuscation you can do, right? And say, okay, well, what will we do with all that data? We can't index it. It's like, we don't have to. Like if you have a syslog server, just anything you can just dump this data to and then point this tool to it, then you can actually start detecting this for $0 out of your pocket. And with that being said, we wanted this to be as user-friendly as possible from an operational perspective, not just for the research community or anything like that, because we are operational security practitioners. So what that means is that if you're using this in your organization, and as stuff comes back and it gets flagged as obfuscated, you can say, okay, this isn't obfuscated, this is good, I never want to see this again, and you can basically whitelist that. And so we have a couple options. You can basically drop scripts into a whitelist directory, it'll hash those, and then never alert on those exact hashes again. You can also whitelist based on strings or regex matching, which you want to be a little careful with so you're not too open with it. But again, we wanted it to be really user-friendly to kind of operationalize this in your environment. So with that being said, you can get the code. It's on my GitHub. It's also hosted on the PowerShell gallery, which means on any PowerShell prompt, you can just type install-module revoke-obfuscation and have it up and running within 30 seconds finding obfuscated PowerShell. And in the tutorial, if you follow on GitHub, it'll take you to the tutorial. I actually included some EVTX files and some other files in there. So actually all the sample commands in the tutorial are actually running against like real data that we produced. It's not actually malicious, but actual obfuscated data. So you can actually see right away how it works and kind of the speed at which it works. In conjunction with this research, Lee and I at Black Hat and DEF CON released this white paper, which is hosted on the FireEye blog there, which is everything I just said, but without having to hear me say it. It's all written. There's less jokes, let's be honest, so you can take your pick there. And then a couple references, again, to some of the previous tools of PowerShell obfuscation, some of the blogs about detecting it, and then, again, the last one here, PowerShell Hearts of the Blue Team by Microsoft. If you have not read that blog, it's a blog post and a white paper that is just a phenomenal overview of all the insanely awesome preventative and detection-based capabilities that Microsoft has put into PowerShell over the past several years, and it's just really, really cool. So, with that being said, that is the end of my talk, so thank you very, very much for listening. And so I think we have 5 minutes or so for questions, so yes?
Did your research attempt to see what percentage of the obfuscated logs were actually malicious?
So if you're saying of all the things that it flagged as obfuscated from our corpus, what was all malicious? Yeah. Most of it actually wasn't. A lot of the stuff that was obfuscated was like code golf competitions and stuff like that. There's a lot of the same stuff. Like if you just like search through the corpus, which the corpus is available also, we made that public. If you just search for things like invoke Mimikatz, just the way that GitHub starts to fork repos, and there's like everyone has their own copy of it, and so some stuff was obfuscated that way. We did see some PowerShell ISE steroids, which was probably one of the original PowerShell obfuscators, which they were doing it more for like IP protection. But we do see some of that data. But in the end, this is looking at data that people have uploaded to public sources. So we didn't find anything that was like groundbreaking. This is really, really, really bad. But I've definitely used it on several engagements at Mandia, and it's been really cool to see it find some stuff some of the stuff we had found through other means, but it was cool to see this model at work against just like massive data sets. So, really good question. Yes?
So earlier in your talk, you mentioned that you could get around the simple character count by just attaching like Shakespeare to it. So what happens if you attach a sufficient amount of well-structured, PowerShell code, and you have a small amount of the obfuscated code inside you? You can possibly make, something that would not trip your machine by like figuring out what that threshold is.
Yeah, really good question. So the question was, in the character frequency analysis, if you have evil code and then have all of Shakespeare's works, then you could actually kind of counter that and it would all holistically look good. Well, could you basically with this model, take a really small piece of evil obfuscated code and then have just massive amounts of full code that's not evil? That would be about the best approach to breaking it. Other than the other concept is, why don't I minimally obfuscate it? Like, again, you don't need 1,000 tick marks. Like, if you know exactly what defenders are keying off of, you only have to put tick marks or obfuscate those small pieces. A really good project that was just released 2 weeks ago at DerbyCon by Ryan Cobb. He's the guy who basically put together Obfuscated Empire, and he released a tool called PSAMSI, which uses AMSI, or the anti-malware scan interface, to basically identify AV vendors that are using AMSI to inspect PowerShell and actually see what portions of the script they're keying off of, so that you can basically drill down and find, of this huge script, here are the 5 pieces that are part of the signature that this AV vendor has, and let's just obfuscate those. And he actually uses Invoke Obfuscation to do just that. It's a really, really cool idea, super smart dude. So definitely a talk worth checking out in terms of like evading the detections. Now, at the end of the day, you might think, well, that's kind of stupid for you to say, like, here's exactly how to evade this thing. Well, you got have some amount of humility and realize that, like, this is only so much, and we're really impressed by the results. But at the end of the day, all it means is that as we find in the wild or come up with on our own examples that bypass this, literally the only thing we have to do is just label those as obfuscated or not, add it back into the data set, and literally hit a button to retrain the model, go get a cup of coffee, and in 5 minutes, there's a new weighted vector that we can plug in. But the exciting thing is that anyone in the community can do that. So if people find different models or different vectors that make more sense, like, hopefully they share that back out with the community and say, hey, this actually works better than what these guys came up with. So that's our hope, that real data scientists will go and do some cool stuff with it, or people who aren't data scientists can start to take this data and play around with it and not scrape GitHub for like a month and a half. So, but really good question. Yes?
You mentioned earlier that APT32 you said was using PowerShell obfuscation. Do you know if they were using your code?
It was definitely my code, yeah. Yeah, kind of APT32 using obfuscated PowerShell. It was pretty evident to me pretty quickly that it was my code. So it was kind of that was the first time I'd seen an APT group using my tool, which was kind of a happy, sad moment. But I don't know. Unfortunately, there's no way to give this stuff out to only the good guys. But yeah, I think the most responsible thing is sharing as openly as we can with the community, and saying, like, be aware this is a thing. How do we come together and detect it? And this was really my best attempt at an answer to say, like, open source, what can people take? How can people take hundreds of hours of mine and Lee's research built on other people's research and use it immediately to help better protect themselves? But yeah, really good question. Any other questions? Awesome. Thank you again very, very much.